Hello, everyone. Morning. This is the best moment for you guys to help me know if the audio is working properly. Please let let me know in the comments if you can hear me well, if you can see me. Kirilo, I, 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 I hope I pronounce your name properly. Working. Christian said it's working. Nice. All right, guys. So I will just wait around 2 minutes. So we usually give the audience 5 minutes to everyone receive the notifications on their cell phones, email, etc. To join the live. So let's wait just 2 minutes. Then I will ping Daniel. I will bring Daniel to the live stream. I'm very excited for this topic today because like Christian and I know there's other people from PBA and Polkadot ecosystem here. I am one of the guys who I develop on Substrate, but I don't know much about Jam beyond the idea, the concept of what Jam is, but I have never seen any code related to Jam. So I am also very excited for this live today because Daniel is working with Jam. He's implementing engine of Jam using Elixir. That is another language that I'm not very familiar with. I know like the advantages of Elixir, some things that he fixes because I have a lot of friends that they are, how can I say, I don't know if they are advocates, but they are very proud of no Elixir. So every time Elixir come to the topic, they Elixir this, Elixir that, a lot of good points about the language, but I have never seen the code. So today I will be seeing two very interesting topics together. That is Elixir and Jam. So I would like to know from Advance if you guys that are hearing me, if you know Elixir. Is there anyone here that knows Elixir, have programmed before in Elixir, or have some familiar with? All right, Antonio said audio it's okay. Nice. All right, we have already have a good amount of people here, so I will bring Daniel. Good morning,
Hello,
Daniel.
everyone. Hi, good afternoon, good evening. Depends on where you are.
Yeah, I said good morning because I'm Brazil and here is 10 a.m. Let's see.
Yeah, I'm in Lisbon. It's 2 p.m. here. I just had lunch. Hi,
Nice.
Antonio. Hi, Christian.
Yeah,
Christian,
Kirilo.
who else is here?
He said he have
Kirilo.
experience with Elixir for a couple years. It's good to know that the audience is prepared for what is coming.
Yeah, we have a mix of some Polkadot fellows with some Elixir people and developers from all around the world. It's good to see everyone. Um, and the idea, my idea of talking with you about Jam is to try to. I think the main objective for me here is to convince you that Jam is not that hard or is not that impossible as one might think when you take the Graypaper for the first time. So for those who are not familiar, there's a specification, a formal specification. Let me share my screen here.
Yeah, before this
Using
live, Daniel said his goal was I want to everyone think that great paper can be easy to read. Then my first thought
yeah.
was okay. I want to believe, but it's hard to believe.
Yeah, and the idea is to make this accessible for everyone, each and everyone. There's a lot of people working on Jam today, and I confess that when first saw this in my life, when I first saw the Graypaper, I like said, "Wow, what is this?" I I completely don't understand anything that is here. I need to read it really, really careful line by line, hundred times
I
to
Daniel, I remember
understand.
one specific phrase you said. I read it 10 times and I couldn't understand. I couldn't pass the first paragraph.
Yes, and you know, I've been working with the Jamixir team. So Jamixir is one implementation of Jam. There are more than 30 teams working to implement Jam in different languages. If you go to these, this is the website, the graypaper.com. You have these resources, and you can see here all the versions of Jam being implemented by different people, different teams, in different programming languages. So we have Go, Java, Kotlin, C++, Rust, and our is Elixir. There's another implementation of Elixir from the Gray Matter
That's
people.
cool.
Yeah, there's a lot of people working on it. We still don't have any production ready version, and it's going to take some time to get there. But the idea here is to talk from developer to developers. So I am an ordinary developer. I am not like a super, let's say, god in developing things. Like, so when you hear those more experienced people talking, usually you get a little bit afraid of asking questions and say, oh, maybe I will say something that is dumb. Maybe I should be quiet. It's very intimidating at the first time. So the idea is that, okay, I passed through this process of like understanding Jam, understanding the Graypaper, and I'm still like every time I read something again, I get new insights about it. So it's not something that you just read and understand once and that's it. So it's a thinking process where you read and then you think about it and then you read again. But one step that is very important to really understand, and this is what I wanted to emphasize here, is the thing that you need to do to understand Jam is implementing Jam. Even if you don't implement the whole thing, if you try to read and implement at the same time, and this is how I personally understood a lot of things. Just reading the formulas won't give you all the insights that you need to understand other things. So, and Elixir is a very interesting language because sometimes you read the formula in the paper and then you go to the programming language and you actually write almost the same thing that is in the paper you write in code. Almost, it's like a translation, but there's no like the code is not different from the formulas, and it's insightful to see that when you read the formula, it's scary, but when you read the code, is okay, and then you say, whoa, it's the same thing. It's the same thing. So, for example, let me go here. Just forget about what is Jam. I want so I want to respond here. What is Jam? What is it for? So there's a lot of if you go to the Jampaper the Graypaper website, there's a lot of lectures here where you can see like a lot of thing Gav himself explaining Jam, and it takes a lot of time to watch all these videos. So these are more technical and lectures about the formulas. But there are also conceptual videos that explain why Jam exists, what problem it is solving, and I can touch into it a little bit today, but this is not the focus of our conversation today. I want to go through coding and showing formulas and how to transform this formula into coding. And as you do it on and on and on and on, you will understand Jam. So it's another path. Instead of watching videos or instead of like looking at, oh, what is Polkadot? Let me understand what is Polkadot, what is blockchain, what is this, what is that? A lot of concepts. I want to take another path and just read the formulas and try to give you the tools to read the formula without being scared about it. And this is my main objective today. And if you can do it, you can read the paper without reading any text. You can only read the formulas and you understand Gem just by reading the formulas. This is the great part of it, because you have a lot of things, like many pages. Like, how many pages do we have? Like, I don't know, maybe 70 pages, 60 pages with the appendix and all this stuff. So 60, 70 pages. It's a lot of stuff here, but there's a lot of text. If you skip the text and go directly to the formulas, you go to the, let's find the first one. Well, they are numbered. Okay, blah, blah, blah. Okay, here's the first formula. You have this. And then when you get here and say, what is this? Oh man, what is X, Y, and M? So this is the point where you get stuck, and you need to breathe and try to get a few small concepts. And if you get these few more small basic concepts, you have this base layer of understanding how the formulas are written, then you can move on until the end of the paper, understanding everything. So just for example, imagine this formula here. So you say you have this here. So let's try to understand this together and see that this is not something. It's explained. Most of the formula, they are explained in like plain English, and then there's a formal specification of it. So what is U? Usually when you have and this repeats many times in the Graypaper. Usually when you have and this is how Gav tries to make us more comfortable as we move on. The first time you see this U, you say, what is U? What is this? Why U and not Y, or not W, or not A, whatever? So he's trying to create names for functions. So what is a function? In the programming language, everybody knows what is a function. So if you create, let me create a simple, I don't know, functions.x file. For examples, okay, I have my functions. So for example, I can have a function that gets sum a plus b and do like return a plus b. Okay, so this is a function. We know what it is in programming language. Functions are definitions that have names and that have parameters and that has returns. So every function is something that gets an input and an output, and that's it. If you go to the paper, you have U, you have A0 until N, so we have any number of parameters. Some programming languages have this ability to have like infinite number of parameters. Some don't, but it's okay. If your programming language doesn't have infinite number of parameters, as Elixir doesn't have, you can simulate it by passing one single parameter with a list, and this list can be any size. Okay, so this is something that you can map. Instead of having like n parameters, you pass a list or an array or something, a structure that can be as long as you want. And then there's this definition. So the definition says that you have all the parameters, whatever parameter is, 0, 1, n parameters. So the response for this function will be, so take the first element that is not new. So this symbol here is new. So for those who never see this in math, you represent new, or the what we call in Java, you have you have the new, or you have new here in Elixir. So some programming languages, they have this new constructor. So basically, this small ball here, like this, is the new. Okay, so every time you see this, say so. So take the first argument, which is not new. So very simple, and there's an example here. So for example, u of new 1, new 2 equals 1. And u of New is new because there's no parameter besides new, so it's new, and that's it. So basically, if I want to implement this function, it's pretty straightforward in Elixir. If I want to, like, imagine that I'm gonna have a list as argument, okay? So this is how you represent lists in Elixir. So if the list is empty, what is the result? New, because if you can find anything that is not new, so the result is new. So basically, this is the first definition of the function. And okay, so if I have this function, there's a first element like this, and there is the rest of the elements. This is how you define in Elixir.
Daniel,
And yes.
can you zoom in a bit?
Okay.
Yeah, I think it's better now.
Better? Okay.
Yeah, way better.
Okay, so imagine that you have this first element and then the rest of the list. This is how you represent in Elixir a list that has a first element and all the other elements like tail. Let's say tail. Usually this is how you call head and tail. And what you're gonna check? You're gonna check if this element is a new. It means, okay, let's keep trying other elements. If it's not new, return it. So if H is not new, then I will return H. Okay. If not, I will call recursively the U function. So basically, I will pass the tail to here again, and then it will try to take the next one and the next one, and this is the implementation. So basically,
This will
you are
just
reading.
will this just pop the non-new element, the first non-new?
Let's create a test for this. Okay. Let's say functions test. Okay. And then def moduli functions test. Do use case describe u1 and test. Okay. Returns the first no new element. Okay. So I am asserting that when I call this, it's 1, right? So let's run this test. Let's see if it runs. Yeah, it runs. Let's assert, let's take, for example, new 3. This should be 3, right? Okay, let's run it again. And it's passing. So what I am doing here? I'm reading the paper. Again, I'm reading the paper, and then I'm understanding what is the formula. What is the formula? What is the idea of the formula? So take a number. The substitute if nothing function is equivalent to the first argument, which is not new, or new if no such argument exists. So, for example, let me write the test for example, if the list is empty, there's no argument. If there is no new argument, the answer is new. If there is just new arguments, the answer is new. Let's test again. Okay, all the tests are pressing. It looks like magic, but it's not. I just did. If the list is empty, return new. If the list is not empty, returns the first argument if it's not new. Otherwise, call it recursively. I mean, it will take out the first, and then we'll call again, and we'll reduce the list until there's no elements left. If there is any single element that is not new, it will return. If there is no element that is new, it will get to this point where the list is empty, and then it will return new. Okay, so very simple, and of course I implemented this. In a more like a functional way, because I could make a for loop, as usually is. If you're not familiar with recursion, sometimes some people struggle with recursion, but you can implement using a for loop. You can like, okay, let's iterate through this list of elements, and this is new? Yes, go to the next. This is new? Yes, go to the next. This is new? No, return. I could do this. It's okay. It would be the same. But what I wanted to show you is that sometimes the formula already it is already, this is the like the iteration. So you iterate from 0 to x minus 1, and then until you find the element that is new. Okay, then it's here. Let's try to read it again. So it's ax, it's one of the elements such that ax is not new, or x is n, means I get to the end of the list. So this is what is written here. Again, you take n number of arguments. You take an x such that ax is not new, and or this v like this is or, you get to the end of the list. X, which is the index, is equals to the last one. So you return the last element. So I could implement like this also. I could implement if you have a single element. For example, if you have a single element, you return this single element. Is the same. This is how I can write the tree. This is, in the end, this is not, it won't return a different result, because if there is a single element and this element is new, it will remove it, and it will call this one. Okay, so I created this case where there's no elements in the list. But anyway, so this is the formula. It looks complicated, but if you read it 1, 2, 3 times, you will understand it. And this goes on. This goes on for all the formulas. So these are all specifications that you keep reading, and as you move on, you see that everything. So this is the first tip. When you read the Graypaper, you must understand that everything that is, if you go to page, whatever page, 196, the formula 196, random formula. This formula here, if there is something here that you don't understand, probably is because you didn't read what came before. So this P and this NC and this W, what is this? What the fuck is this? So this is defined before. So you have to find where is W defined. So if you move on the paper, if you go on the paper formula by formula, when you go to the next formula and you understand all the other formulas, you understand the next one because you understand all the other before. And they were defined before. So you need to read formula by formula and understand each one by one. So this is how I started to understand the Graypaper. First, it starts with some definition, some like basic notations that you're gonna find all through the paper. But one thing that sometimes it's very useful for people to go and read the paper. So there's a one side note here. This website here is the Graypaper. It's a Graypaper reader. It's a way to, because you can download the PDF and read it, and it's fine. But you can go to this website and you have this, you can take notes and you can see different versions because the versions keep upgrading. So if you take one note in one version and then the note got lost in the next version, so this reader helps you to keep reading the next versions without losing your notes. So this is the, if you wanna, I'm gonna put in the chat the address of the Graypaper reader. Okay, so the first, let me zoom out a little bit. The first part, when it starts to talk about notation, it first explains. So this section is very important. Besides, Gav don't even give a lecture about it. It's very important because you need to understand what are the letters that are going to be used along the paper. And if you have this in mind, it's not hard, but you have to keep in mind that there are these, for example, when it uses this calligraphic typeface like this one, or like this one, or this, these are functions. So if you go to the last part here, you have this appendix where basically you have this all these letters here. So you have these ones, and then you have this one, and then you have the functions, and then you have the utilities, externalities. So if you understand that each letter will represent one of these, and basically, if you count, there are many. So basically, I was realizing that Gav used all the letters from the alphabet. If there were just one more formula, it wouldn't be possible because there would be no no more. Actually, the Z is not here, so maybe there are one or other letters left. But if you go to so basically, what you need to understand, you have these sets, or there's sets or groups of elements. Let's say, of course, everybody's familiar with n, which is the integer. So we are familiar with these sets in math, but mostly we know we know n, we know z, we know q and r, and that's it. We don't know anything else. So Gav defines some like versions of these sets. So for example, n is all non-negative integers. Every time you find n, means in programming language, in the case here, for example, here in let's take sum, for example. I take two numbers or integer. I take an integer and another integer, and then I return an integer. So this is in Elixir how you define this a plus b, for example. So this is the specification of the function. So this function gets two numbers. So when you go through the white paper, you see a lot of times this. You see on and on again. You see, wait a minute. Let's go to any function, for example. Let me take every function, any function that you see, for example, this p, whatever. I don't know what is p, but I know that the arguments of this P will be a tuple. So this curly brackets, it's also defined that in the first chapter. But when you have this curly brackets like this, means a tuple. A tuple is like a limited list of elements. It will be something like this: A, B, C, for example. This is a triple. Okay, this is a quadruple. A tuple means the number of arguments that are grouped into a limited amount. So you have, so if you take where is here? So it takes a tuple of elements of the type W, which I don't know what it is, doesn't matter right now, and returns an element of type D that is like, what is this? Well, it's complex. Okay, so you go to what is D? D, you go there, and then you can go to the definition of D, or you can go to the last page that I showed you, and it's going to explain what is D. D is very simple. If you are a programmer, you already saw D many times. It's just maps, dictionaries. What we used to in Elixir, they are represented like this: A1, B2. In JavaScript, they are something like in JavaScript something like this. Yeah, this is how it's written in JavaScript. You create like an element that is something like this. Is it like this in JavaScript? I don't remember.
No,
I've been
it's
coding
two
Elixir
dots.
for, yeah, it's something like this, right?
It's two dots. A, two dots, one.
Yeah,
Yeah.
but you can also use this. I think it's
Yeah.
just like a
You
JSON, a
specify a
JSON
string.
file.
Exactly.
Yeah, like this. Oh, okay, something like this, right?
Yeah.
Okay, B and then okay, but you know what it is. This is the D. So every time you see a D, you understand that it's a map that has keys and values. In case of JavaScript, you can't have keys of any type, from what I remember. I don't know if you can have keys. No, you can actually. You can have any kind of key, right?
Yeah, it's weak typed,
Yeah,
as
you
it
can
says.
have any kind of key. So basically, when you see D, whatever, D with this KV, this arrow, means it will be a dictionary. The keys will be of the type key, and the values will be of the type V. So let's go back to that any formula that we saw anywhere, somewhere that I don't remember anymore. Here, for example. So this dictionary here will be, keys will be of the type NS, and the values will be of the type NG. Oh, but what is NS? What is NG? You go there, you see it's defined. N, N, S, NS, and oops, and NG. It's here. And you can click and goes to the formula. So what is NB, NG, and whatever? Basically, when you have N with a subscript, it means that it's an integer, but it's limited. It's not any integer. It's limited by a size. So for example, in this case, it's maximum 2 to the power of 64. So basically, it's 2 to the power of 64, which is like this huge number. I don't know. It's so huge that I can't even. But basically, it's when it's n 2 to the power 32, it's from 0 to 4 billion, 294 millions, and so on. So basically, this is the definition that you have here. If you go to dictionaries, and you're gonna see, okay, what is a dictionary? Oh, this is the formalism. You have a dictionary, you have keys, you have value, and then you denote that it maps from the domain. Yeah, when you say domains, means the set of value that are possible for input, and the set of values that are possible for keys in this case and for values in this case. And then you have like a, whatever element is in this dictionary, if there is some key that leads to a value, then so this what is saying here, the dictionary members must associate as at most one unique element, which means if one key takes to one element, there's no way of the same key going to another element, right? Because it's a dictionary. If you say the key is Daniel, for example, let's imagine that we have a dictionary here. Let's wherever, for example, let's say D equals, okay, the key is Daniel, and the value is my ages. Let's say ages. Okay, I'm 45, and let's put here young. Young is 25. Okay, 25. Am I right? How old are you?
27.
27. Whoa. Okay. So there's no way of Daniel having two ages. I can have only one age. This is what is saying here. Whatever element in D, so each element basically is this double of key and value, key and value. So this is an element. So if you take any element that has a key to a value in the dictionary, there is doesn't exist another value that the same key takes to. So for example, if I put here Daniel goes to 44, in the end, depends on the programming language, but I assume that in this case, Elixir will probably take the last one as the truth. So I can run this code here, but anyway. So basically, this is what. Let's go to a terminal. Then I have. How do I run? I never use this, but run Elixir REPL. It's EX. Yes, I always forget. I never use this, but anyway. Okay, so let's take, for example, ages. You see, it took the last one, and this is the truth. It warns me and says Daniel will be overridden in the map because there can be the same key pointing to different values. So basically, what Gavin is doing here is like making this formally specified. It's saying whatever D belonging to this set of this, so the dictionary, there is no way of a key that takes to a value, and there's another value that the same key takes to. So basically, this is what it's telling.
Are basically
then,
math notations, right? If we are familiar with math notations, you can transform it into code because after
exactly,
like seeing
so you need to
the
learn.
formula.
Exactly, and you need to learn what each symbol means. For example, what this symbol means. This little a in the upside down. It's whatever D, all elements in D, all the elements belonging. So this E means belongs. All the elements D that belongs to D. Then whatever key value belongs to this D, because what is D and what is D here? So let's try to remember. D is the set of all the possible dictionaries in the world. So D is a very generic type. So basically D is the construct that we have here in Elixir. You can have any dictionary. So imagine all the dictionaries possible in the world. This is the D with the capital D. And what is D? D is one dictionary that I created, a single dictionary that I created. And what it says is, doesn't matter what dictionary you created. Sorry. Doesn't matter what dictionary did you create it. Whatever dictionary you created, whatever key value in this dictionary, you have key pointing to a value inside your custom dictionary. Then this is this E on mirrored E means exists. So exists with the exclamation means not. So when you have the exclamation, you have the negation of it. So it doesn't exist a value with the this tick here. I don't know how to say, but it's just to refer that is not the same as V. Is another value different from V. It doesn't exist this V whatever that the key leads to this V in that belongs to the same dictionary. So this is more or less what is saying here. And
The most sorry, Daniel. The most crazy part is that this is making sense, you know.
yeah, exactly, and everything makes sense. Everything makes sense. You just need to understand, and of course, for the first time you read, you don't know. You get stuck when you see this symbol because you never saw the symbol before, and when you see this a symbol, for example, I never saw this symbol, this like because this one was created. Some of them are like very ordinary math notation that everybody uses, so it's more like common through all the maths. But some of them were created by Gav, so you have to like, and you don't know sometimes the difference between what he created and what already existed before the Graypaper. So basically, you need to read from scratch and try to understand what are the things. But as you pass through the first 3 pages, mostly you saw everything that you need to understand and see to understand all the rests. So basically, when you say when there is this, what is this? But it sometimes they explain in plain English as well. So we denote this set disjointness means you have two sets. So set basically it's I would say taking Elixir for example 1 2 3 4 set 1 actually. Yeah, this is the way we create a set, because sets don't have like repeated elements. So the difference between sets and lists is that when you have a set, if you have, for example, 2 4s in the list, when you transform to a set, it will remove the duplicated, and you can have just one single element of each value. The same value doesn't repeat in a set. In a list you can repeat, but in a set you can't. So if you have set 1, set 2, for example, we have two sets, and then it defines here what is the means that the intersections of two sets. What is the intersection? What are the elements that are the same in both sets? So basically, if you take this set, and this set, what is the intersection? It will
2,
be
3, and 4.
yes, 2, 3, and 4 exactly. So the intersection is 2, 3, and 4. But the disjointless means when there's no single element that is belongs to both sets. So every time you see this A, like whatever, I don't know how to name it, like pirulito, let's say in Portuguese, pirulito. This pirulito, A pirulito B means there is no single element that belongs to A and B at the same time. Okay? And that's it. Now you know what is pirulito. So every time you go, and the next time you are all walking through the white paper and say, oh, A pirulito B, oh, can be, if there is two elements that belongs to both sets, there's something wrong. So this is what you must keep in mind. Okay, but I spent quite a lot of time here, uh, only on the formulas, math formulas, because I want to stress, because nobody did it before, from what I understand, because sometimes they get this from gradient. They take this from for gradient. They say, oh, everybody knows this, and sometimes some people don't know too much. So this is why I wanted to stress here. But let's go a little bit further, and you see that. So these are there are other definitions, like for example, when you have this snake pipe, and you have this basically, let's recap. You have sets, you have functions that we know in the programming languages, have functions that have inputs and outputs. You have like sets, which are like groups of elements, as we saw here. And then you have numbers that can be like integers, it can be unsigned integers or signed integers. And then you have dictionaries. All of these is part of any programming language. So any programming language that you use, you have all these symbols, or all these types. So you have dictionaries. Sometimes they're called maps. Sometimes they're called like hashes, whatever. And then you have tuples, which are like the two elements. In Elixir, they are represented like this. This is a tuple. 1, 2, 3, 4. Oops. Tuple. Yeah, they are kind of different than lists. They can, of course, you can transform a tuple into a list and a list into a tuple, but they are different concepts. But they, in some way, they are similar. But the difference is that usually lists are the size of lists are indefinite, and the size of tuples are fixed. You have 2 elements, you have 3 elements, you have 4 elements. You know beforehand how many elements you're gonna have inside it. So this is the difference between tuples and lists. Usually lists, all the elements are of the same type. So you have a list of integers, you have a list of objects, you have a list of whatever. In case of tuples, you can have different types. You can say, oh, the first element is of type N, the second element is of type Z, or whatever. And then you have sequences, which is, in this case, what I call list. So Gav calls sequence. So basically, this is a sequence. So this is let's put this way. Sequence is this. So this is a sequence 1, and then I have a sequence. The set 1 takes the sequence and transforms it into a set. Remember, the sequence can have repeated elements. So basically, it's a sequence of whatever elements you have.
But in the end, it's a list, right? Or can be a different type of. That's why he used this
Yeah,
sequence.
so sequence is how Gav calls. In Elixir, we call this list.
Mm-hmm.
But sometimes you can call it array or whatever, because
Good.
array is a way to implement a sequence, because you can have
Mm-hmm.
a pointed list that you have the way it is structured in memory is different, but sequence is a more generic way of talking about arrays and lists, because arrays and lists both are sequences.
Mm-hmm.
Okay. In Elixir, you don't have arrays, actually, from what I'm aware of. Actually, maybe there's a way to implement array, but usually you don't use too much. You use more lists, because every time you just want to be more efficient in terms of implementation. Sometimes you using array is more efficient. Sometimes using list is more efficient in terms. If you want to access the first element always, using list is more efficient. If you want to access any element in a constant time, array is more efficient in terms of computation complexity. But yeah, so basically it says this, that you have the sequences and then you have the like ways of telling, oh, you have a sequence of n elements and you can get all the elements until the second one. In this case, you have, let me put a little bit bigger so you can read it better. So for example, you have a sequence 0, 1, 2, 3, and then you have 2, dot, 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 2 means take all the elements until the second. Okay, 0 and 1. And if you have 1, dot, 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 plus 2 means you take the first element and then you take 2 from from the first element. So you take 1 and 2. And then you can have, there's another notation that you take the last whatever elements somewhere around here. And then you have this, what you call construction, which means you take all the elements from the group. So for example, you have this, all the elements x0, x1, x of size n, means you can, if you, let me just, yeah, you want to define, so instead of, you take any function and then you apply this function to each and every element in the list. So instead of writing F0, F1, F2, F3, and so on, you just write this way. So it's a way to say, in the programming language, is a for loop.
Like a map.
It's a for loop. Yeah, you can consider, if you have an original list, it's a map. You're right. So in JavaScript, you have this map. So for example, if you take this sequence enum.map, and then you have the sequence, which is the sequence, and then the function. What you're gonna do? Okay, I want to multiply by 2 every element. So for example, let's put it here so you can. So if I want to map sequence one, yeah. So basically, you take every element of the sequence and then you apply any function. In this case, it's a generic function that takes one element, and then, so if you understand this, if you look at this, it looks complicated, but if you translate to programming language, you already know the concept. It's a map. It's a you iterate through a list and you apply something to each element of this list, or array, call it. And then you have, like, for example, this I with this little snake with I belonging to X. What does it mean? It means that these elements are ordered, which means if I have this notation, means that the elements are in order. You don't have elements out of order. It's just a requirement. Sometimes during the Graypaper, you're going to see that, oh, you have this array of elements. They are ordered. If they are not ordered, you reject the block, reject the information, because it's not correct. So this is a way to, in just 3 characters, say this is in order. So mathematically speaking, you're saying this is in order. And these double snakes means they are in order and there are no duplicates. So for example, if you take this sequence here, it is not ordered and there are duplicated numbers. But if you take the sequence 1 and you remove the 5, for example, and then remove this, for example, this is ordered, but it's not, there are duplicated numbers. and this one is ordered and doesn't have any duplicate. And then you have like editing. So for example, if you every time you find this like whatever uh, mountain symbol, whatever it is, it's just saying you are adding these elements, you are concatenating these two elements. So basically, when you have in Elixir, you can do this by, for example, you have this, let's say, list one, and then you have list two, four, six, six. And then if you want to like join them together, like glue them together, you have L1 plus L2, and then you have this concatenated with this. So this is what this symbol means. And if you have this symbol over here, this whatever means, take the take the element E and put it in the end of this list. So for example, if I have L1 and then I have a value, for example, A, which is 5. So when it has the symbol, I don't know how to say this symbol here. This one,
Garden
this
gate.
like garden gate, whatever. So X garden gate, Y means take X, which is a sequence, take Y, which is an element that can go into the sequence, and put it in the end of the sequence. So basically, you take the 5, the A, you put inside like a simple sequence, and then you like add it to the end of the, the previous created symbol. So again, these are all the definitions that come here, and the editing, and when you finish this, you can start, and then like after almost 1 hour. I'm sorry for taking a little bit longer, but I thought this was important because I don't know how you're feeling, Young.
I'm very comfortable. Like I notice that this is a complex way to explain simple programming. So like you are showing formulas and a lot of stuff when translates to code. It's simple. When I see the code is way simpler than the notations. So yeah, I'm feeling
Yeah,
comfortable because
I
now
would
I'm
put
being able to see that.
Yeah, I would put differently. It's not that is more complicated. It's just a language that you don't speak,
Yeah,
and it
exactly.
looks complicated because there are symbols and some tokens that you never saw before. So the first time you look at this, it looks complicated because you didn't know it before, and of course it's complicated. If you take a child, a 5-year-old child, and show this child letters in an alphabet that this child never saw before, like Japanese, it will say, "Oh, it's too complicated." No, it's not complicated, because if you show the same character to a 5-year-old Japanese child, this child will understand immediately. So it's not complicated. It's just something new that you never saw before. And then when you see for the first time, it looks odd. It looks like I don't know what it is. But when you see this symbol over and over and over again, you start to get familiarized with it. And then it's very powerful, because with just a single symbol, it has a lot of meaning. So it's a very interesting way of explaining things without telling a lot of words. You just put something in front of you and you understand everything. So this is the idea. You need to understand what all these symbols mean, and for the first time you look, it's going to be difficult because you have to memorize all of them. There are so many of them. There are so many letters, so many like this snake and this one and this one and this one. So the first time you read, you understand. But the next time this symbol appears, you say, "Well, what was that?" You have to remember, and then you remember again, and then you remember again. And then on the third time you see it, it's not more difficult anymore. It's very clear, and this is how it works. So, for example, um, let me take this E here. This is a function that usually uh, you take some any arbitrary object or value, and you serialize this value to a binary. So basically, it's a way to transform anything into your code, anything that you programmed into a binary that it can be that can be transmitted through the network. Because in the end, you're going to transmit a lot of data through the network. So imagine that you have a block. So the block, so let me take, for example, let's go to the block definition, okay? Okay, where is the block definition? Here. What is a block definition? Very simple. A block definition is basically, there's two parts, H and E. So basically a block is something very simple. If you go to the block, it's a struct that has two fields, H and E. H and E. H and E. I think this is
Very similar to substrate, basically the header and extrinsics. Yeah.
exactly, yeah. Well, but I don't need to even compare it to anything. I'm just defining that the block is a structure that has something that is H. I could call H here. Of course, I'm trying to like create more like easy to understand language than like letters, because sometimes memorizing letters is more difficult. But and then you have E. But basically, this is what B is. So I can say B equals H and E. And that's it. Okay, but what is E? E. So the type of the first element, the header type, is a B. It's it's a H. Okay, so let's find where is H defined. It's defined. Where is it? Okay, it's over here. If you go, and then you have H. Oh, it's defined here. What is H? Okay, H is this. Then go here. And then you go to block header. Okay, so let's just take this out of the way so we can see only code here. Okay, so I have my header, and then and you see we have these formula comments here because it's actually pointing to the formula in the paper. You have the P HP, the parent hash, and then you have the HR, which is the prior state root. And then you have all this. So basically, a header is a struct that has like many components. So it's in JavaScript, I would say it's an object with properties. Very simple. So basically, you have a header that has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 properties. Okay, what is the first property? The first property is a hash. So this set means hashes. So it's a hash 32 bytes hash. It's a value that is hash, something that we are used in the crypto land, like wallet addresses or something like that. And then you saying that the hash, this value, so the value of this first field here is basically you take the parent. So if you see PH means the parent of this block. So the parent of this this header, which means the header that came before it. There's a way to hash it, and the way you hash it, you take the whole structure, you encode it into bytes, and then you hash, and then you have a hash. And this is the value that goes in the parent, the HP of the next block. So this is something more like blockchain knowledge. If you never heard about like blocks and a header, maybe you are a little bit confused here. But basically, you're saying that you take the parent of this header, the parent of this block, you encode it, you hash it, and then you put it here. Okay, what is the next one? So HX, it's another hash. So it's the hash of the extrinsic of the block. So imagine that remember that you have a block. you have this block. The block is constructed by a header and an extrinsic. The extrinsic are the instructions. So basically, let's take this way. You are I am creating my blockchain, and the blockchain, if you can define like it was defined in the yellow paper, if you can define a blockchain in one simple uh, formula, this is the formula. Where is the blockchain? This is the blockchain. So it looks so crazy. What is this? What is this and this and this? Okay, very simple. You have something in the world which you call state. You have some information stored into your computer. Any information, whatever it is. This information we call state. You have this information that is recorded into your computer or in the memory of your computer or whatever. And then you have a block, which is a bunch of new things that you want to apply to your state and change it. So you want to change your state to something else. You have your computer, you have your memory, you want to change it to something else. Okay? So you have this previous state, you have the changes that you want to do it, you put it into a block, and then you apply what you call the state transition function. So you apply this function, which is this, I don't know what is the name of this in Greek, if anyone knows the name of this letter. But anyway, you apply, and then you get a new state. So basically, if you go to the code, if you create a new, let's say whatever, s.ax, so dev module x. Okay, you have a function. So let's say this function is I will name it add block. Okay, add block. It takes a block, and I know that I like the AI because it already knows what I'm thinking. But basically, you take a block, you take a state, and then you return a new state. So basically, you for example, you want to say that the new everything is defined here. What is the state? The state is composed by all these elements. So this is, if you go to let's go to our code, and you understand very well. Let me just close this, and oops, oh, I closed it. Okay. Let's go to this. This is so if you take our commit log, this is the first code that I wrote when I started to implement Gen. I started with this. This is the first lines of code that I created. If you take the take the repo here, you're gonna see that there's, if you look at the source, no, it's lib. You see, there's just a few files here, all of them. So basically, I have a block, I have a header, I have a state, and I have a extrinsic. I have only this, like, say, let me remove this one because I created just for, oops. These are just boilerplate stuff, but basically everything that I have in my system, this is the first commit that I did when I started to create Jamixir. So let's take a look at this. You have a header, which, by the way, is just all the elements that you have here that I showed you, the header, all these things. I didn't even know when I started to write this code, I didn't even understand what each one of these elements mean. But I didn't need to understand because this is the definition. So I just created the definition that follows what is in the gray paper. And as I started to implement, I will understand each one of these elements. I don't need to understand it beforehand. When I go and write code, I understand, okay, this is the header, has all these elements. I don't know why they are here, but probably when I start to implement the functions, I will understand why each one of these is here. And this is how I came to understand everything. Um, but you can start without knowing because it's math. The math is defined. So age is here. Okay, age is here. Doesn't I don't know what is like epoch. I don't know what is epoch. It doesn't matter. But there's something called epoch. And what is winning ticket marker? And you go on and you start to see the concepts on and on again, and then you realize that, okay, now I understand. But you can implement, you can write code without understanding everything because the code can be mapped to functions directly. So let me take the add block function. Let's take the state, for example. I created this add block. So this one, this is the state transition function, basically. And this is how everything started. So this is the state transition function. I have a block. So basically, I'm going to take a block that has a header and has an extrinsic because, as stated before, these are blocks. Wait a minute. What is a block? Block is a part that is a header and is a part that are an extrinsic. And what is an extrinsic? An extrinsic have these 5 parts. Okay, so what are these 5 parts? You have tickets, you have judgments, you have pre-images, and then if you go to extrinsic, what is the extrinsic? It's here. You have the tickets, you have the judgments, you have pre-images, you have availability, you have reports. I'm just taking the code and writing what is in the white paper. So E equals ET, EJ, EP, EA, EG. ET, EG, EP, EG. You see?
But all these judgments, tickets, as this stuff was at the gray paper.
Everything is defined here. Everything is defined here. You're gonna see, but
Oh, I see
look.
now. Yeah.
I'm in. There are 350 formulas, but if I'm in formula 14, I already implemented 5% of the gray paper because you just need to go to the next formula. Okay, you have block. Block, I already have. I implemented. It's here. This is block, header, and extrinsic. Done. What is the next? Extrinsic. Extrinsic is this. And then you implement extrinsic. You come here. These are the elements of an extrinsic. You have the tickets, judgments. What comes inside a ticket? I don't know yet, but it's going to be clear later. Doesn't matter because you can move on. Okay, what is state? Okay, state. What is state? You have all these elements. And each one has a Greek letter to represent it. I put the Greek letters here because it keeps appearing on and on again, so I can remember which Greek letter belongs to each concept. So, for example, you have authorization requirements. They are explained here. You have the delta, which is the part that deals with the accounts. So, what is delta here? Here, services, accounts. Here in Gem they call services, but it's like accounts. So data belonging to someone or some service or some smart contract. And then you have this. So I define it state. You have state and you have all these elements, and then you have a function that takes this state, this block, and then you get the next state. Okay, so let's move on. How do you transform the previous state into the next state? I mean, okay, what do you need to transform? What data do you need to transform each part of the state to the next state? So, for example, Formula 16. These are the dependencies of the state transition function. It means to know the next tau, I think it's tau the name. So the tau line here is the next one. So remember, this is the previous, and this is the next state. The next is always represented by this line over the letter. So to know what is the next, where is tau here? Here. This is the tau, because this is one of the components of the state. The next state is the sum of all the components, okay? So if you change alpha, beta, gamma, delta, I don't know all the names of the Greek letters. I don't remember the name, but doesn't matter. I know that this is pi and this is phi and this is like whatever. some of them I know better. Lambda, kappa, whatever. Ho, I think this is ho. And but anyway, it's just way to name them. And every time you see a Greek letter, you know that we are talking about some state, data into state. And this is the beauty, because sometimes you want to talk about functions, and then you take like these letters, these uppercase letters to represent functions. Sometimes you want to talk about sets, and then you take these math notation. Sometimes you want to talk about state, and then you take the Greek letters. So this is how it keeps communicating different concepts along the paper with different notations, thus for you to be very familiar with what it's talking about. Because if it uses only like Roman characters, it will be more difficult to represent everything into a single formula, because it will be very confused. So this way, you are saying, okay, this is a state, and there's a next state, and there's a function, and this function takes the previous state, the block, which is represented by a structure that has a header and an extrinsic, and transforms to the next state. Okay, but how this transformation occurs? I still don't know, but I know that to take the next time, this is time, okay? This is how to represent time in state. The component, if you look at the component, what is it? Okay, the x, okay. Most recent blocks and time. So most recent blocks is beta, and the time is this, I think is tau. So if you want to represent time, you use this time. What is time? Is like what you call block number in usual blockchains. So basically, what is the next block? The next block depends on the header. It's just telling this. Depends only on the header. If you look at the header, you can know what is the next time. You don't need to look anywhere else. Okay, great. Then I create I will. This is my state, and I know that I need to update. I'm gonna to return a new state that has different components. The time component. Where is the time component? Is recent time. I think this. Yeah. Let's call time. It's called recent time, but let's call it time just to be more precise. Okay, later we changed names. We changed this name to time slot. But anyway, okay, I want to update my state. I know that I will update the next time. The next time will be something that updates time. I will call a function to update the time, and this function depends only on the header. So I would just pass the header as an argument. And then I take this one, and then I can put it here if I want. Actually, it's already exists. Actually, it's already there. Sorry. So the time is update time. You take the state time, because it depends only, actually it depends, it doesn't depend on even the current state time. It doesn't depend on, you have only the header. It depends only on the header. It doesn't matter what is the previous time. It just matter what is the header. Okay, and then you have this beta, whatever, daga. I don't know how to call this, but I want to update the beta. I want to update the beta, the recent blocks. I don't know how to update it yet, but I know that to update it depends only on the header and the previous beta. So I create a function called update beta, whatever. And then I have the previous state, because it depends on the previous beta. I can take the previous state dot recent blocks. It depends on recent blocks and the header. So I pass the header. Okay. And then this will lead me to beta daga. Okay, so beta daga, whatever. And then I will have this beta, the next beta, the beta, next beta, whatever, next beta, depends on the header, update, next beta, whatever. And then depends on beta daga, depends on C, which I don't know what it is, but someone is creating C. So if you see C here, it's being calculated depending on this, all this stuff. So you need to calculate this. Oh, it depends on this W asterisk. Oh, okay, so let's calculate this. Oh, it depends on. So if you go through all of them, you see that you're just looking at this 16 or 15 formulas, you can create all the functions that needs to be executed to transform the previous state into the next state. You know, is it clear? Yeah, are you following me, or you
Yeah.
got
No,
lost?
I could understand. Yeah.
Oh, so let's take, for example, this n here. What is the n? N is the entropy pool. So, okay, how do I update entropy pool? Next, entropy pool equals, okay, update entropy pool. Depends on header, timestamp, and the previous entropy pool. So header, state, recent time. I love the AI because sometimes it knows what needs to be done. I don't know how, but yeah, maybe because it's watching us. But anyway,
Daniel, I noticed that this whole like architecture kind of inherits the idea of the substrate of generic types of manipulation of stuff, right? Like you don't know what is, but you know how to manipulate this thing between functions and process and transitions functions. Doesn't matter the type of this is, but you know how to manage this, right?
exactly. Yeah, you don't need to know all the details, but if you have the clear rules of what things belong, what things depends on what things, you can
Yeah.
like keep writing. And then of course, this formula 16, if you go to if you read formula 16 here, you see that the next time depends on the header. But what part of the header? It's not specified here, but if you go on and you're gonna see somewhere, blah blah blah. Let's go a little bit further. A little bit further. So sometimes the Graypaper is not written in the most easy way to implement it, because sometimes I'm not sure if, for example, maybe this section here that is talking about the virtual machine shouldn't come here because it doesn't matter for now anything about the virtual machine. So this is like distracting us from what we need to do right now. But there's this whole chapter talking about virtual machine that we don't need it right now because we are talking about blocks and we are talking about extrinsics, and then suddenly there's something called virtual machine. Why do we need this right now? We don't need it, but it's here, and sometimes you got confused. But if you go on, ignore, and then you go this, and then you have, okay, let's go back to the header. Oh, great. You have these components of the header, and then you have this timestamp. If you go to the timestamp, you're gonna see soon. Let's create the block. Let's create the next time. What is the next time? The next time here is what is in the header. So basically, you have you have like next time. What is the next time here? It's just what is in the header. What is in the header? Time. You have this field in the header. If you go to the block, if you go to block, and if you go to header, oh, oh yeah, this one, time slot index. You have this field. So just take it and put it on state. There's no rule. There's nothing. Okay, so that's it. You just did it. You just transform what is the next time. Of course, there will be some formulas that will validate it that you didn't put some wrong time in this field later. So this is some
Because
validations that you
there will be another specification that specifies that this time must be beyond these or the rules,
yeah,
right?
it can be, for example, it can't be a time that is before the time that already passed. So I can't say, oh, now is October 10th, and the next time will be October 9th. No, it's impossible because October 10th already passed. So now can be October 11th or October 12th, but not October 9th. So there's somewhere that will validate. But here, you just define it, and
Mm-hmm.
it works. And then again, and then you have this saffron state, and then you have all these components, and this is how you go on and on and on and on and on, and you keep implementing formula by formula. If you take a, let me get, let me go to the main. If you go to our most recent um, code, okay, state. Oops, state. And you see that we already implemented almost everything. So basically, you already have the implementation of the add block is the same. If you look at this and look at the structure that I showed you just before, empty, you see that is completely the same. You are just like taking things and basically calculating the next whatever, the next so formula 24, formula, let me go here again, formula 16, formula 17, formula 24, formula 25, formula 17. So look, the update the latest state root and update whatever. So this is what we are doing. And if you go into this, okay, now it's formula 82. Okay, what is formula 82? If you go there, you're gonna see it explains in formula 82 how to update the history. How to update the history. Very, very simple. You take this beta daga. Okay, what is beta daga? Let's try to find it somewhere. Beta daga. Beta daga, what is it? Um, it is exactly equals beta, except that the last element, so take the size of beta minus 1, which is the last element. So basically it's saying here, you change all the elements. You keep all the elements the same, but you change the last one. On the last one, you put the value that is on the R of the header. That's it. It's saying take beta. So this is how it's written in Elixir. Beta daga equals beta, except that beta daga, the last element, is equal the header, the R. So the R in the header is this prior state root. So basically, you take all the blocks, because actually the beta is a sequence of blocks, is a history of blocks. So you take all of them and you split into all the blocks and the last block, like this. You have like a part that takes all the blocks, and then you have the last one, and then you change it. You put all the blocks that came before, but the last one you change. You put on the state root, the information that you put on the state root, it's the information that comes in the header. And this is how you update what is here, what is written here is what I wrote here in a function. Of course, if you're not familiar with Elixir, maybe it's a lot, but basically I am just pattern matching, because I'm passing like a recent history as an argument. And the recent history, if you look at this, recent history has a list of blocks, because it's just a list of blocks. And these recent blocks has some information like a header hash, the accumulated result, state root, work report hashes. So there are some a lot of information. But the only thing that needs to change is that you take exactly what it is, but in the last one you change the S. You change the S component. The S component is the state root. All the rest remains the same. So imagine that you have this. So imagine that you have like recent block. You have a list of this. So this is what I'm doing here. A recent block. You have 4, for example. And then you have header hash, whatever, 1, header hash 2, header hash 3, and header hash 4. And imagine you have this. And then you have the state root also. Let's see, whatever, 1, for example. 1, 2, 3, 4. What I'm saying there is that take this, split into this and this, then take the state root of the last one, take whatever is in the header dot, what is the field? Header private state root, prior state root, So you transform this, you transform this something like this. So you had this, and now you have this. You just change one value of the last element on the property state root. This is what I'm doing here. I need to take all this because there's no easy way to split the elements and take the last one. This is how you take the last element. You need to call this split function. And this is the size of the split. So basically it puts the first part here, the last part here, and then the last part you have one element. That's why you can have this last block. And then this means take all the fields in the last block and repeat them into this new created recent blocks, except that the field state root is S.
Nice. And now, at what stage are you at? In which formula are you implementing now?
Yeah, it's a pretty good question actually. We are. I would say that we did like 2/3 of the formulas implemented. So if you, we have actually, uh, if you, we have something. We always comment through the gray paper. If you if you look at our code, for example, this one that you have all these formulas here. If you run this bash implemented formulas, it will go through all the code, find this pattern
Mm-hmm.
of formula whatever, and then print all the formulas. And then if you copy and paste
300.
this, yeah, actually there are these are the ones that we implemented. But if you look closely, you see
Ah,
that there are
okay.
some missing number. So for
Mm-hmm.
example, we didn't implement it from 226 to 290. We didn't implement anything. These are just
Okay.
the implemented ones.
Mm-hmm.
If you paste here and then you go here, there's this formula that basically
Mm-hmm.
tells which formulas we still need to implement. So basically, we did everything up to 157, and then there's a little bit here, and then there's a little bit in the end, the appendix, and yeah, there are some, let's see,
Mm-hmm.
almost 2/3 implemented. So there's a lot,
Nice.
some work
So
to do.
these gaps is formulas that probably was not required to implement the further ones, right? That you did.
We need to implement everything.
No,
This
I
is
know, but
our.
for example, you did the 100 and didn't the 95, for example. The
Yeah.
100
Because
didn't
not
need that.
all of them are not. Yeah, not all of them require some prior, some previews too.
Yeah.
So, for example, especially the appendix. So this is something that we, because the appendix doesn't. You don't need to implement anything else to implement the formulas in the appendix, because they are
Okay. Mhm.
completely, let's say,
Independent.
self-sustainable. So, for
Hmm.
example, the encoding, how to encode new. Oh, encode new is an empty, is empty. So basically, okay, let's create a, like, let's
Ah,
say
okay. So some formulas in the gaps probably will depend on these formulas that you
encode.
did.
Yeah, let's say I want to implement encode here, for example. This is okay. I want to implement 290. So this is how I encode, and then the argument is new. So the first element is new. So this is just empty. Okay, actually, I'm gonna do it because it's a binary. So this is okay, implemented. Formula 290 implemented. Then I come here and then say formula 290. Okay, next one. How to implement, if the element is a binary. So if def encode x when is binary x, then just return x. Because if it's binary, I don't need to encode it. It's already encoded. Basically, all the binary is a binary. You just need to encode when you have something that is not a binary. Okay? So, okay, 291 implemented. Okay, let's go to the next one. If you have a list of elements, you just encode them and then concatenate. Basically, if you have like encode x when, or something like this. Let's say list. If an if it is an empty list, it's it's empty. Okay. If there is an element, then I encode the first element, and then I concatenate with the encoding of the rest of the list. Something like this. This is what is here. And then okay, now it's a number. How do we encode number? And then you, okay, let's take. If the L is 0, and then and you move on. How to encode a header? How to encode a header? Encode header. Def encode header. Okay. How to encode a header? You just encode the encode unsigned. There's a definition somewhere about encode unsigned. Where is the definition of encode unsigned? Somewhere. EU header and encode S. Can you help me to find encode unsigned here? Encode unsigned.
There is a very good question on the comments. Please let me know when you can
Oh,
answer.
here, encode unsigned. Oh, look, encode unsigned. Okay, so encode a header, and I take the S of the header. What is S? If I go to the header, I have the S. What is S? S is the block seal. Okay, so basically the encode of the header is the encode unsigned. Here, encode unsigned of the header. Concatenated. Actually, this is how you concatenate binary. It's kind of different. With the encode of the block seal, like this. Okay, so implemented 302. And then how do we encode unsigned? Okay, so we encode the parent and then So you see, all the formulas are specified. Oh, what is E4? E4 is defined here. E4 is defined over here. E, L belongs to N. So E4 means E4. And so on. What is the question?
I will put here on the screen.
Could you give a high-level characterization of the cycles of the algorithm? I don't know if I understood correctly the question. What do you mean by cycles of the algorithm? Explain better. Maybe it's asking about the complexity of this algorithm. Is this the question?
Yeah, I also don't get it. Cycles of the algorithm. I don't know if he's mentioned like how many times these functions are connected, but I'm not quite sure if it's that.
Yeah. Okay. So there will be, of course, after you implement this, you have to run and you have to see if it's efficient or if it's not efficient, and you have to find ways to improve your code, make it more efficient. But right now, I would say that I am not worried about performance. So this is something that is very important. It's something that needs to be done. But most important than understanding and making it performatic at the first hand, I need to understand the concepts. And the way I understand the concepts is by implementing these formulas. Now I know the concept because I implemented it.
Yeah, I think this
And then,
connects with this comment.
yeah, exactly. So it's if you see the paper, because sometimes you see paper and then you see, oh, how this is transformed into code, and was my intention to show that you can transform this into code very easily. Of course, not easily, but the more you do, the more you see that it's not that hard, because the functions are simply transformations. You have like, okay, I'm transforming something that is y. Y is a binary. So I learned before. I saw y many times until the moment that I now, every time I see y as a set, I know it's a binary. It's a binary. It's just a structure of bytes. Nothing uh, complex. In Elixir, you represent it with where is the Yex, like this. You put this, like, for example, it's a sequence of bytes that can be a string. Essentially, you can have a string like A, B, C, D, or you can have like instead of representing letters, you can represent in numbers from 0 to 55. For example, I don't know what is this. Sometimes when you don't have, if all the numbers are strings, it prints as a strings. For example, maybe, yeah. Sometimes it's interesting because it was like 130 and 130. Yeah, 1, 2, 3, 1, 2, 3, and 1, 2, 3. I don't know why. Yeah, sometimes 1, 2, 4. Yeah, you see, when the element is a letter, for example, like this, 50, 51, 50. This is the ask table. It's just numbers that translates to characters sometimes not, but it's just a sequence of bytes. And then why is this sequence of bytes? Because sequence was defined before. If you go to the first page when we started, you see that y is a sequence of bytes. Bytes, it's a data that has 8 bits. Everything is defined over there. It's called octets because sometimes byte is more like a computer thing. Octet is more like a abstract definition of something that has like 8 bits.
Diego pinged back on the question he mentioned. So he asked first, call. Yeah, you put there right. This was his first
My
one.
question is a high-level characterization of the chained execution and independence of the different stages. Uh, I would say that I just can't answer this question right now. I'm not yet completely capable of answering this question. But what I can answer is that, and what is in the Graypaper, and this is what is interesting because Gav explicitly calculated this for us. Let me just get a glass of water. I am here speaking for like 2 hours, and the throat is getting dry. Okay, so if you take these formulas here, you see that you have all these components. So basically, you have to calculate all this stuff, and they are completely some of them, not all of them, but some of them are completely independent. So for example, you can calculate the 16 and the 17 in parallel, because to calculate the 17, you don't need anything that you calculated on the 16, right? So you can create threads and in Elixir, it's very easy to create different threads and calculate things to spawn the process in different processes and then calculate them separately. And then after you do it in a separate way, you join everything together. So in JavaScript, you have like promises in different programming languages. They are done in different ways. But this way, we know that the dependencies are more or less defined here. So basically, you depend on the header. So most of the things depend, because remember, when you are transition a block, you depend on the previous state and what comes into the block. So basically, everything depends on these two things. But there are parts, there are subparts. You don't need to all the parts to calculate all the subparts. So, for example, if you want the beta part of the state, so this part of the state, because the state is composed by all these elements, the beta part of the state can be calculated just with the header. So you pass the header, you pass the previous beta state, and then you can calculate the next one. The I don't know the name. Looks like an N. The N, the next N is the header, the tau, and the previous tau and the previous N. So you pass these three things and then you calculate. So there's no dependency with anything, any other calculation. But for example, this one, you depend on something that you need to calculate before. So to calculate C, you depend on W, and you depend on this V, and you depend on this all this stuff. And then to calculate, so you can't calculate C before calculating W asterisk. So you need to calculate W asterisk, and you need the E, A, and then this pi, no, it's phi. Yeah, I think it's phi. Or ho, I don't know. I'm terrible at Greek letters. But you have this letter, and to calculate W, it depends on this. So you need to calculate this. And to calculate this, you need the G, EG, and then you have this. So there is a small sequence here that you need to follow, because you need to calculate this, and then you can calculate this, and then you can calculate this, and then you can calculate C, and then you can calculate this. So there is a sequence, and these are the stages that you need to calculate in order. But once some of them you have to follow this order, but some of them are independent. So this is independent. This is mostly independent except for this. Yeah. So for example, the kappa, you have dependency only on this one. So you calculate this one, the 23, and then you can calculate the kappa. Some of them are more dependent and some of them are less dependent. I don't know if this was your question, but yeah. But up until this moment, you will so let's, after following all this line of thought that I gave to you, I think we are 2 hours of webinar. Maybe we should stop for now. I don't know how tired you are. Yeah, but it's a lot of information. But I would like to take questions right now, and because this is the most important thing. How are you feeling after all these explanations, and what is the thing that still is not clear for you that you wanted to know?
So I encourage you guys to let in the comments. But while you guys do that, I want to ask you on, from the last explanation, it sounds that, so it's not, I was thinking that was linear, so all the next functions depends on stuff that was previously defined. But in the last formulas you was showing, some functions depends on future functions.
Exactly. Yeah. You're right. There is not exact. So yeah, the ordering could be better. Yeah, the order is not exactly an order that you need to follow one by one. I would say that 80% is in
Linear.
order, but there are some tricky parts that maybe. So sometimes what we did when we were implementing was that, Oh, we depend on this C. We don't know how to calculate this C because it's 5 chapters ahead. So we just create a mock function that's okay. This is calculate C. I don't know what this does. I will know. I will know later, but I will mock it and I will call it, and then it's okay. It's fake that you implemented it, and then you finished. And then when
Mhm.
you really implement it, everything will fit. So we keep sometimes. So this is how we along the way while we were developing the Jamixir project. So if you want to know more, jamixir.org. There is our Telegram that you can go in. We have the GitHub, have an email that you can contact me, and also the Twitter. If you want to follow us on Twitter, let me just put the call here. Maybe as a banner. I don't know. Yeah. So you can follow the project. So basically, while we were implementing, we sometimes we face this situation that, oh, I don't know how to implement this yet. It's in next 3 chapters. So we just put that the formula and then move on and then move on and then, oh, now arrived the moment that we are going to have to implement this thing that we expected to implement like 2 weeks ago.
Mhm.
So this is the process. But sometimes no. Sometimes you start to implement something and say, oh, you need to use this function. Oh, we already implement this last week. Now I know why I need to use this because before
Mhm.
I didn't know why this is useful. Now I understand. So you see,
Mhm.
some things you don't know and just move on, and sometimes you implement without knowing exactly why this is useful. But when you use it, you see, oh, this is useful because of this. So writing
Yes.
code is a very intelligent way of understanding the gray paper, even if you don't want to
Mhm.
like create a very performatic implementation of it. Just by using your best the programming language that you work that you learn that you know better. Doesn't matter which programming language you are using. Actually, there are, if you see here, there are, as I showed you, there are 15 different programming languages being implemented. Doesn't matter. What I like in Elixir is that sometimes, as you saw, it's pretty like the formula is the
Straightforward.
code. The
Mhm.
formula is the code. So let's take for example, especially the last ones. When you go to the appendix, for example, the Merkle tree stuff, it's it's almost the code is almost identical to the to the
Specification.
formulas. You should look at
Mhm.
the code, you look at the formula, say, oh, it's the same. It's just like you are
Mhm.
just this is math, this is Elixir, but almost no difference.
That's cool.
If the specification is correct, your code is correct. If it matches one by one, so this is what
Mhm.
we are trying to do. And one more thing, of course, not all of you are is able to come, but we are organizing a meetup here in Lisbon on October 21st. This is the link, if I'm not wrong. So we are organizing a small meetup. Let me add the banner. Yeah. If you want to join us in real life, for those who are in Europe zone or even those who are in Lisbon are like intimated to come to our event. It's gonna be fun. We will like talk with other Jam implementers in other language. So I would love to hear from other jammers what are the parts that they are struggling more. Whoops. And gonna have some talks, have some food, and also in for those who are planning to go to DevCon in November, We're gonna have DevCon. For those who are not familiar, DevCon is like the biggest, one of the biggest conference, Web3 conference for like blockchain developers. Is the original Ethereum conference where people meet to work together. There are hackathons. There are a lot of like meetups and talks and everything. So this year we'll be in Thailand, in Bangkok, from November 12th to November 15th. So for those who will be there, we are planning a jam event, 3 days, where we are going to meet and discuss and learn from each other. And it's going to be just after the Sub-Zero event. Sub-Zero is the conference of all the Polkadot ecosystem. So basically, everybody from Polkadot, from different backgrounds, devs, and business people, part chain owners, part chain communities, substrate developers, Polkadot SDK developers. So all them together, trying to like learn from each other. And there will be many. It's Sub-Zero, if I'm not wrong. Sub-Zero, yeah. I don't know what is the website, but anyway, Sub-Zero 2024, maybe. Yeah, yeah. It's Google doesn't know the rest, but yeah, yeah. Maybe this one, Sub-Zero Bangkok. But this one is March. No, it's not
Yeah,
the
I
one.
when you sent me the post from on the forum, I tried to look for the date and I couldn't find any updated information, but it
Yeah,
will
yeah, yeah.
is
Because sometimes these decentralized stuff are not that efficient as we want it. So there are some people organizing the event, but the best way, the best place to find, it's called Sub-Zero Reset. I found it. Here it is. Sub-Zero, no, Sub-Zero Saigon. No, 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 no. Sub-Zero Reset. Sub-Zero Reset. Maybe if I search aqui, here. Yeah, this is the right place. Subzero.gg. You can apply to speak. You can apply as a partner. If you want to sponsor, you can get some tickets. Basically, this is the website. Yeah, I already purchased my ticket. Actually, I don't think you need to pay for tickets. You just need to subscribe. And if you are doing something, or if you, it's Saturday, November 9th in the, I don't know, this is a Thailand address. But anyway, and one more thing that I think it's worth mention, we're gonna have a new Rust bootcamp next week, right? Yeah.
yeah, exactly. 16 will be the kickoff, and you will have the opportunity to learn with me and Daniel about substrate development. And I think most of you guys that are here are familiar with, but it would be a very good opportunity to build a blockchain from scratch. And I think is one of the most interesting, in the most better way to start at Polkadot, and understanding the substrate environment, because you build everything from the scratch with teachings of step by step. It's very similar to how Daniel did here, explaining each piece of concept and showing code of this concept. And it's the same approach, but it's text. It's a text bootcamp, a whole asynchronous bootcamp. So you guys are all invited. Let me also put the link for this here in the comments. And I think that's it. Very How can I don't even know how to name the feeling, Daniel, because as I said in the beginning, I thought it was like a very challenging idea of make me feel and everyone think that gray paper could be easier. And I must admit, not because you are my friend and I'm hosting this live, but I'm really understanding. Like I really think I if I would implement this, I know how to start it, how to read it. For sure, I'm not very familiar with the math notations, but I don't know. It now it's not sounds that complicated as it sounded before. I remember first time I saw the gray paper was like, oh my god, this is so confusing. But now I really got a grasp of how to translate this into code. So I'm really excited. I'm very happy that this was possible. I don't know how
Yeah, and
everyone
I,
is
I
feeling.
would I would advise you. I would advise you to take take a random formula on the gray paper and try to understand it. Take a random formula and try to understand the way I explained it. Okay, if you don't understand something that is in this formula, probably is because there's something defined before that explain that specific concept. So go there. And then if you have here and then there's something you don't understand, go a little bit back until the point that, okay, now there's a formula that all the concepts that are here are familiar for me. And then try to understand. And then when you understand, then you go to the other formula that it didn't that depended on that one, and then try to understand. And you're gonna see that little by little. And no, don't try to understand just intellectually. Try to write some not code, real code, but try to think in coding. Take your favorite programming language, Python, JavaScript, whatever, and try to put this what is there into the code instead of just what just looking at the formula and thinking. Write it on the code and see if it's correct. And if you want, reach to me and say, Daniel, I tried this, but this part I don't understand. Can you explain me? And then maybe we can do another section, maybe a workshop. So this would be the next step. So if we could be like doing a whole day workshop, I could do this first introduction of 1.5 hours, like explaining the basics and how to navigate through the grade paper, and then give you some exercise. Okay, so go exercise. Let's try to read a random formula, or even if it's not read, the first 50 formulas, take one of them, because maybe the first are less complicated than the last one. Probably the more you go deeper into it, the more complicated it gets. But sometimes even the last formula that I showed you, there's like, for example, that specific formula. Remember, where is yeah, this one, for example. Look at this formula. This is so simple. There's nothing here. Like, it's just telling that this function in code, well, that I call encode, when the argument is new, returns an empty sequence, basically nothing. If it's new, it's nothing. Simple. And if you are encoding a binary, it's just a binary, so you don't need to encode it. So basically, this formula is very simple. And there are some formulas that are more complicated. Okay, what is this? Oh, this is so complicated. Yes, but if you take case by case, you see that it's not complicated. But sometimes there's a lot of things to be done. So, for example, let me just give you one last example. Here, the encoding. This one. So this 314 is the specification of how do you take the state. Remember that we were talking about state, because if you go to the code, you see that state has all these components. You have the recent history, you have the Safro, you have all this stuff. How do you transform this into a binary? Because you need to, in the end, you need a binary, and then when you have a binary, you need to transform this binary into a single hash, which is the representation of your state in a hash in 32 bytes. So how do you transform this structure of hundreds of fields and values and arrays and a lot of stuff into a single information? Basically, this is specified here. You take basically the first one is the one, oh, the C1, the C1. So remember that it's a dictionary. This is the key, this is the value. The key is C1 and the value is encoding of the X of all the X's that belongs to alpha. So if you go to our code and take it, C1 here, C1, look, 1, 2, 3, 4. You see, 1, 2, 3, 4. You look at the formula and look at the code, is the same. Encode this variable size. This means variable size because when you have an array that has variable size, the way you encode that, the first information that you put is the size of the array. So you put like, okay, there are 33 elements. So put 33 and then all the elements. So this is how you encode non-fixed size of elements. You say there will be 33 elements. Then you put 33 and then all the elements after. So you know that you're going to see 33 information that you have to read. So basically, the alpha, you take all of them and then you encode it. Okay, and how do you encode? What is the 2? Simple, it's just encoding of this P. Is this a Greek letter? Yeah. Okay, encode the authorizer key. Authorizer Q, and the 3 is the encoding, and so on. So if you see the implementation here, you see that all of them are implementation of the, okay, how do I implement, how do I encode the entropy pool? Entropy pool is one of the elements. This one, entropy pool. You have a definition of how to encode the entropy pool. It's defined here, because the entropy pool. Where is the entropy pool? It's one of these. Maybe if I go to the entropy pool and then I go to encode, I will see the formula here, 67. So 67, right? No, this is calculate. This is encode. Yeah, basically, yeah, it's just 4 numbers. So basically, you just encode all of them like this. Just put them. But anyway, this is the next step. So take your time, take some formulas, try to implement it, try to, just for fun, just for exercising. And you see that you are able to move on. If you want to contribute to Jamixir, you can, like, okay, you don't need to understand the whole code base. You just take the Graypaper, see one of the formulas that we didn't implement. If you want to contribute to an open source project like ours, or maybe others, if you don't want to work with Elixir, go to the website of the Jam clients. Find one of the teams that maybe you can join as a sporadic contributor. Take one of these. Oh, I'm familiar with Haskell. Okay, go talk to Altimario. Send there are contacts here. You can send these people, or these are these contacts. You have Python, you have TypeScript, you have Elixir, any programming language that you, maybe there's Java, there's even Java. Just send an email, say, oh, I saw talk from Daniel. I'm not familiar with Elixir, but I like Java, or maybe I like JavaScript or TypeScript. There's no JavaScript actually. There's just TypeScript.
I looked for JavaScript, but there's just TypeScript.
So maybe you can create your own implementation. You don't need to finish. You just need to. It's a very good exercise to train your skills, to train your ability to read some formulas, to create code, and have some fun.
Mm-hmm.
And or if you want to really contribute, join us in our Discord, join our GitHub. We can open the code for you, and you can read the code, and you can understand what you are doing. If you look at the, or maybe you don't want to implement anything, but you want to, like, let's take some code and let's take the formula and see how they implemented it. I just want to learn. Okay, you look at the code, look at the formula, and you're gonna learn. You can read our code and learn how we did it, so you understand better the concepts of the Graypaper. So probably in the next months, more implementation. All the implementations today are closed, so most of them are private because there's a prize, and some people are like keeping their implementation closed until the prize is over. But most of them will be open source. Actually, all of them will be open source, is a requirement. So you'll be able to see the implementations, but I'm pretty convinced that at least the first version will be the less complicated to understand, because when you move on to the next milestones and start to implement some optimizations into code, the formulas will get a little bit more, the code will be a little more complicated, not because it's complicated, but because you need to be more performatic, so you need to do a lot of stuff besides what you need to do to make it more efficient in terms of memory consumptions and so on. So sometimes the most efficient code is not necessarily the most easy to understand code. And I understand that when you start to get the first milestones being delivered, this is the moment when you can look at some code and understand the Graypaper better, just looking at code.
Yeah, definitely. After today, I'm sure that looking at the code implementation is way
Yeah.
easier
And
than.
join our Telegram. I don't know if I sent you. Yeah, I sent the link. Let me send the link again. So join the Jamixir Telegram or any other. There's the official. Where's the? Wait a minute. So if you go here and then you have resources, you will have these matrix rooms, the Jam matrix rooms and the Graypaper room. There are these two groups here that you can follow here on Element. Let me just show you. Yeah, the Jam chat, this one. And yeah, there are not so many people here. There are just 291 people. But you can join this chat. It's completely open. Gav is very active here. So if you have questions, you can ask here. If you are afraid of asking directly in the group, because like maybe you feel not so comfortable, I'm pretty starting, I don't want to ask dumb questions, send me questions in private. No, I don't mind. And yeah, let's jam together.
Nice. Thank you, Daniel, for your presentation. Thank you, everyone, for your presence here, for be learning with us, and see you guys. Bye bye.
Bye bye.